dot product and the cross product. Yeah. The dot product is the official name, yeah. So it looks something like V dot W and V cross W. That's what they would look like if you ever see them written down. The dot product gives very much a scalar result. So a number, just gives a number, which is related to like force in a direction. It's more of a physics thing than the maths thing. We're just looking at the applications of it. And the cross product gives a vector. And interesting enough, that vector, does anyone know what that vector's relationship to the two we make it with is? Perpendicular. Yeah, it's perpendicular. It creates a perpendicular vector to the two original ones. And you're talking about in three-dimensional space here. Not two dimensions, obviously. Okay. Wouldn't make sense with 2 dimensions if you think about it. Yeah, it would come off the screen. It would come towards you. So it has to be into the 3rd dimension. Okay. So we'll just, I'll just leave this as... We'll leave this aside for a second. We'll just look at the dot product again, just in case we forget how to do it. If we have 2 vectors, let's say V is, what one did I write down? 2, 4. And W is 1 minus 3. So V dot W, this times this. What did we do again? It was
2 times 1.
Yeah, 2 times 1, so the top 2 multiplied, plus 4 times negative 3, yes. And that's 2, take away 12, which is negative 10. So that negative 10 is something got to do with the force applied in a particular direction. If you did it the opposite way around, VW and WV, they would work the same both ways. So it does have that commutative property. If you just did it the other way around, multiplied V by, or dot product V by W, you'd get the same answer. What it really is useful is when we talk about the angle between 2 vectors. And this, there's a nice, and it's using this theorem, A dot B is equal to, make sure I get it right, the magnitude of A times the magnitude of B times cosine theta.
Which one is that?
That's the use of the dot product. Yeah, we're still on the dot side. I should probably put a line here. The cross has crossed into the dot. But anyway, yeah, thanks. So that's direct relationship between vector A, vector B, and this angle between them. There's now a relationship between those two. It is usually more usefully used or just rearranged to find the actual angle. If you do a very quick rearrangement, you can find that cosine theta is equal to what? A, yeah. Yeah. Yeah, so A dot B. So let's, so that's use. So we'll actually try and do one of these. We're going to look at, let's look at 2 other vectors. Let's go 3-dimensional vectors now. Let's go 2, 2 minus 1 I've written here, and W, 5, 3, and 2. I'm going to look at the angle between these 2 vectors. I want to find the angle. How do I find the angle between these vectors? I'm going to have to do the dot product and find the magnitude of both. So the magnitude of V, perhaps we'll do first. How do we get the magnitude of a vector? We square and add, don't we? And then we square roots. So kind of like Pythagoras' theorem. 2, 2, 2, 2, 2. What is it? 3. It looks like 3, yeah, because 4, 4, and 1 gives 9, and the square root of 9 is 3. And what's the magnitude of W then? Not quite as nice, I don't think so. 5 squared plus minus 3 squared. Plus.
Is it not root 7?
This one? Yeah. Minus 1 squared is positive 1. I think I have 38 here. Root 38, is it? Okay. Okay. So that is the magnitude of both those vectors. And now we have to do the dot product of the both. So V dot W will be, what do I do again? Okay, I multiply 2 times 5. And I add 2 times negative 3. And I add, yeah. and I get some sort of answer, which I've already worked out. What is it? 2? Yes, 2 makes sense. So 10, take away 6, take away another 2. Yep. All right.
3 by root 38.
Yeah, so now I use this formula. I want to find the angle between these three-dimensional vectors somewhere out in space. What's the angle between them? It's 2, the dot product, divided by the magnitudes multiplied. Okay, and from here, obviously, this is not a known angle. This is going to be a calculator question. Use your inverse cos of 2 over 3 root 38. You can do that if you want, if you have your calculator there. You should get around, if your calculator is set to radians versus in degrees, you'll get two different representations of the same angle. It's around 84, I think. 84 degrees or 1.46 radians if you do cosine inverse that.
1.46 rad.
Fantastic. 1.46 radians, so almost 90 degrees.
I have a question.
Yeah.
Do you have to write down rad after 1.46?
It'll probably tell you format.
Yeah, it probably would say which form to put it in. So the question might earlier on say between 0 and pi or something like that, and then you know it's in radians.
1 radian is equal to how many degrees? No, so the idea is that 1 radian is pi, so 3.14.
No, 3.14
Pi radians is half of the circle, 2 pi is a full circle of radians. So 3.14 is 1 radian.
What? 3.14 is 3.14.
3, 4,
180
yeah.
degrees.
Yes.
Yes. 3.14
Yes.
radians is that half circle.
So you want to know what?
You said it was 1 radian. Wait, so 3.14 radians is 180 degrees. Yes.
Yes, yes. So you can divide 180 by 3.14 to find what 1 radian is. It's not a nice number.
Yes.
Yes.
It's a circle.
For the purpose of this.
Technically, if you do it in like the area of a circle or something, it wouldn't be in radians necessarily.
Okay. Let's move on. One quite often asked thing is what happens if it's a 90-degree angle. So what do we expect the dot product of two vectors with a 90-degree angle to be equal to? Think cosine. Cosine 90 degrees is 0. Sine of 90 degrees is 1. Cosine 90 degrees is 0. So that means if A dot B, if A dot B is equal to 0, then A and B are perpendicular. So we get a 0 here. You get cosine is equal to 0. It doesn't matter about their magnitude. Right. So that's the dot product. The cross product is a little bit more complicated. We don't now create just a scalar number out of this. We create that vector. That vector we create now is a 90-degree angle. I can get rid of this, hopefully. A 90-degree angle. Luckily enough for us IB students, we are given the formulas. So you have the scalar product here as well. The angle between two vectors, that is just given here. They've actually broken it up for you.
This would be in geometry still.
And this cross product, or vector product, sometimes it's called. Let's put that there. Yeah, I'll be in the geometry section of the HL. Okay, so we have it's got a definition: V times W, V cross product W is quite a complicated looking thing. So this is when V is V1, V2, you got 3 numbers here. W, you've also got 3 numbers. Yeah, and they're not combined in kind of they're combined in a matrices way. But we can just use this formula. So it's V2, W3, take away V, make sure I get this right, V3, W2, and then that'll be the I direction, V3, W1 minus V1, W3. You do not need to remember this, but we will need to know how to apply it. V2. Okay. So as you look at this, maybe you see some kind of pattern where in the first line, when we were dealing with getting the first coordinate, or the I coordinate of the vector, you don't actually deal with the first two numbers. You almost like cover them up and only deal with V2, W3. And V3, you do like a cross thing here. You see that? So I'm looking at V2, W3 and V3, W2. So you do a cross here. This is why it's called the cross product. And then if you're looking at the V2 line, which is a bit harder for me to show, but if you blank out these two middle ones, you cross these two. And then if you're looking for the V3, the last, the K, you cross out that and you look at just the first two crossing. Okay, so I think an example here might be helpful if we look at two vectors and do the cross product. Let's call V, yes, Isha?
Because of how they figured out, does that mean that like which vector goes first matters?
Yes, it does. So that also means you can put as a side note here, I was going to talk about this, is VW the same as W cross product V? No, it is not. It is not the same. You would get one that has a relation to it. I think it'd be going in the opposite direction maybe.
So V231 and W231 are either side.
Yeah, let's look at an example and maybe we'll get the hang of it. We actually have numbers. It might be a little bit simpler. So if I do V, so I'm looking at, this is my formulas that I have. I'm looking at trying to get the cross product, trying to get a perpendicular vector to these two three-dimensional vectors. And I go, right, I slow down and I go, right, how do I do this? I need to get this first coordinate here. And to get that first coordinate, I look at the cross product of these two. But I have V1, V2, V3, and I have W1, W2, W3. I can refer back to this. So V2 is the number 3 here. And that has to be times diagonally by -5. And I subtract V3, which is, sorry, this one, V3, and W2, I'm here, 7. So I can work out that's going to give me the I direction of the vector, the first. 3 minus 5 is minus 15. Take away a 28, gives minus 43, I think. Not particularly nice number. So that's the first coordinate. Now I do that for all of them. So I'm looking at my second line here, which is V3, which is 4. V3, W2, so I'm always crossing over like this. And take away V1, W3, V1, W3, 1 minus 5. So there's a minus here. So that'll give 13, I think. If I do the 8 minus 5 gives 13. And then I do the last one, which is going to be V1, W2, V2, W1. So V1 is 1 times 7 minus V2, W. No, oops, that's a 3. Yeah, it's going to be 1, isn't it? 7 take away 6, which is 1. Okay. So we've created a vector. Yeah, it's a bit slow. There's a matrices method.
That's a whole different class.
Don't think it's necessary to know the matrices. It gives the same answers, so no need to complicate matters at the moment. We'll just do this method, which is the cross, and this is the formula that's given to us. So why don't we use that? There's something called the right-hand rule. If A was or let's use V and W. If V is this one, and W is this one on my right hand, V, W, then this one is the one you've created.
Well, yes, that is how a perpendicular line works.
Yeah, it's just, well, but sometimes we need to think about when that is turned upside down, which we'll talk about later. So this is the plane, or there's a plane here, and this one shoots up off this direction off it.
I get how it looks.
Yeah.
I just don't like how we have to get to it.
I don't get it. I get how you get to it. I don't get how it looks.
Yeah, we'll just think about it. Like think about two.
Think about the corner
two vectors in three-dimensional space, if you have two vectors in three-dimensional space, they might be like, Philaine, they might be like this, somewhere in two-dimensional space, they're like that. And the third one is,
So they have to be attached?
yeah, they'll have to cross, yeah.
Because the vector is a value. It's not like a set coordinates.
It's like where they cross and then the third one. Okay, there's a couple of other notes we want to take on this and then we'll look at. There's a similar formula here and this one deals with cosine. So if we have the magnitude of the cross product, the magnitude, yes, so this one deals with cosines. Oh, it's here, yeah. So if we do the magnitude of the cross product, so this, but we got the magnitude of it, so minus 43 squared plus 13 and so on. If we get that, and we have the magnitude of A and B separately, it links up with the sine of the angle between them. And you can rearrange that in the same way that we rearrange the cosine one. So that'll get the angle between two vectors a different way. And interestingly enough, at the end here, if we get the magnitude of the cross product of two vectors, we actually get the area of the parallelogram they make. And all these are given in a formula booklet, HL, so they're there. Okay, let's apply some of that now.
Wait, just any parallelogram?
Any